9, exactly. So chapter 9 is all about these questions here. You all have the chapter 9 notes. We're going to be looking at inferential statistics. So far we have covered, if we don't know our mean or our proportion, we can estimate it. That was chapter 7. If we do know our mean, and we want to know if our population differs from the general population in some way, we can compare them by doing a hypothesis test. That is chapter 8. And now we're looking at 2 samples to see if they differ or not. So that's chapter 9. We're going to start off with 2 proportions. And again, these are what we're looking at here. There are a couple of requirements for 2 samples. Again, they should be independent, simple random samples. And you have to have at least 5 successes and 5 failures in each. Okay, so this is a little bit more complicated because now we have 2 groups. So now we know 2 things about each observational unit. 2 variables. First is what group they're in. The second thing we know is whatever the variable is that we're studying. So kind of the response variable. So for example, I wanted to know about, let me pick something good. So cats and dogs. So I want to know if the average weight of cats is higher than the average weight of dogs. I would take a random sample and of animals and of cats and dogs. And the first thing I know about each animal is whether they're a cat or a dog. And the second thing I know about them is how much they weigh. So that would be means, right? Quantitative data. So I would know which group they're in and their weight. Or say I wanted to know about I don't know, what else is something good? People who are students and people who are not students. And I want to know, whether they ride bicycles. So, or whether they voted in the last election. That's something a little better. All right, so then the first thing would be their group, whether they're a student or not a student, and then the second thing I would know about them is whether they voted or didn't vote. So that's more of a yes/no thing. That'd be a proportion. But either way, you know 2 things about each observational unit, what group they're in, and the actual thing you're trying to study. Quick reminder from chapter 2, super important. I will have Alexa, go ahead and read for me.
Correlation does not equal causation. When can we say one variable affects other? There are 3 possibilities for differences between the groups. 1, coincidence, shoe size, and test scores. 2, cause and effect, attendance and grade. 3, confounding variables, or variable HRT and heart disease.
Right. So, so first of all, when can we say that one variable causes another one? There's one specific situation where we can do that. When we've done what?
Experiment.
An experiment. So this is when we've done an experiment, and we randomly assign people to different groups. So we do an experiment. Randomly assign people, or assign to a group. So this is really hard to do because you can't exactly take an animal and say you're going to be a dog and you're going to be a cat, right? You can't do that. So it becomes kind of tough in many ways. But like Alexa was reading, right? It could just be if there is a correlation between 2 things. It could be that It's just a coincidence. Like, say we do a bunch of tests, we have a test, and we look at people's shoe size, and it happens to be that the higher shoe size corresponds to a higher test score. That does not mean that having a big shoe size means you're going to do better on the test. That was just a coincidence, right? And that happens in life sometimes. Two, there could be a genuine cause and effect, like attendance and grades. Typically, people who attend more do get better grades. Or it could be that there's a compounding variable. So if you remember from chapter 2, we had hormone replacement therapy. People who were taking hormone replacement therapy tended to have lower incidence of heart disease. But when they did an experiment and randomized some people to a group to either have HRT or not, it turned out that to be the opposite. But what was going on was people who had HRT tended to be more affluent because it was optional. So because of that, they tended to have better exercise regimens and have a better diet, which led to lower incidence of heart disease. So there could be a compounding variable causing both things to occur. So just kind of in the back of your mind to make sure you're kind of aware of the fact that just because things are correlated, you can't say that one causes another one automatically. You have to kind of look at if there's an actual random experiment going on. Okay, so here's a null hypothesis. Null hypothesis is always no. In this case, no difference between the populations. There's no difference. That means they are what?
Equal.
Equal. Exactly. So write that in. The first thing you're filling in the blanks are your H naught. P1 equals P2. It's also sometimes written as P1 minus P2 equals 0. Right? The difference between them is 0. Pooled samples. Okay, so in your notes, you're going to have a population proportion. So that's going to be P, or P naught. You have the size of the sample, which is N, and the number of successes, that's X, and P is equal to X over N. So you fill those into the blanks. But then below that, they talk about the pooled sample. So the pooled sample is P bar. It's when you have two samples and you combine them together. So let me give you an example. I take a sample of folks and say I take a sample of a bunch of students and say 5 out of 8 of them own dogs. Then I take a sample of another group of students, and this time, say 9 out of 12 of them own dogs. So that is I have my first sample, I have my second sample. My pooled sample would be if I put them into one big group. If I combined all of them together, then I'd say, okay, well, all together I have 5 plus 9, I have 14 dog owners out of a total of 8, 12, 20 people. Everyone kind of following? So my pool would be 5 plus 9 dog owners out of 8 plus 12 people. So I'd end up with 14 out of 20 as my P bar. And then Q bar would be 1 minus P bar. Yeah.
So the pool sample is just combining the...
Combining into one big pool. Yeah, exactly. All right, so do lab problem number 1. Find P hat and Q hat, and then find P bar and Q bar when you have the following. So for the first one, P hat, you got 20 out of 36, which is 0.555, well, if I round, 556. And then Q hat would be 1 minus P hat, 0.444. And then you had P bar and Q bar. So P bar is you take your Successes, 18 plus 20 successes, out of a total of 60 plus 80 people, and you end up with 36 out of 140, which is,
I think it's 38.
sorry, I did it last class too, that's so weird, I don't know why. And you ended up with
0.271.
271,
Mhm.
great. So then your Q hat would be 1 minus 0.271, or 0.729. And again, I do want 3 sig figs on all of your proportions. Good. All right. The test statistic. So everything else in the tests, in the hypothesis test, stays the same. It's what you expect to get. What you observed. P hat 1 minus P hat 2 minus what you expected to get. P1 minus P2 divided by the standard deviation for 2 proportions. However, and a quick comment, since we do expect that they're the same, P hat 1 minus P hat 2 is 0, this just goes to 0. So really, it's just this part here. I should do a different color. However, you don't need to do any of those at all because you can just use the 2 prop Z test. And we're going to see just how easy that is in just a second. So let's pop to the next page and do an example. Vaccination rates. I'm going to drop out all of this. And take a look at it. So let's get a reader. Jason, go ahead and read.
In the nursing home study mentioned in the chapter opening statistics today, the researchers found that 12 out of 34 small nursing homes had a resident vacancy rate less than 80%, while 17 out of 24 large nursing homes had a vaccination rate.
Yeah, vaccination rate.
My bad. Of less than 80%. At Alpha 0.05 test the claim that there is no difference in proportions of the small and large nursing homes with a resident vacancy rate of less than 80%.
Great. So first we're going to find the part where they're talking about a claim, or they're looking at testing, or they're looking at or a question, or they're trying to conclude something. So where is that?
The last one, test.
Yeah,
right?
test the claim. Does everyone see that? I'll do that in quick, since I've been doing those. Test the claim. What's my claim? There's no difference in the proportions. So first of all, now I know that it's not a mean, it's a proportion. Everybody on board?
Yes.
With the resident vaccination rate of less than 80%. So what's up with the less than 80%? Is that my claim somehow? Less than 80%? What's the less than 80% stand for?
Isn't that just the vaccination rates for both those proportions?
Yeah, exactly. That's just what I'm asking. Your nursing home, is your vaccination rate less than 80%? Say it louder.
Yes.
Yes, okay. Is your vaccination rate less than 80%?
Yes.
Is your vaccination rate less than 80%? Yes? You gotta say it to the camera.
Yes.
How about you? Wow, you guys have horrible vaccination rates, so less than 80%. Is your vaccination rate less than 80%?
Yes.
Yes? Everyone has a less than 80% vaccination rate. What about you? Is your vaccination rate less than 80%?
No.
No. Okay, good. I want to stay in her I want to stay in her nursing home because they have their vaccination rate is not less than 80%. But this lady less than 80%. That's the question you're asking in the nursing home. Does that make sense? Has nothing to do with any of the numbers you're going to be using to do the computations. It's simply the question that was asked. Good? All right. Our claim is, the first thing I do is find my claim. So then my claim is that there's no difference in the proportions of small and large. That means that their proportions are what? There's no difference. The proportions are what?
Equal.
Equal. That means the proportions of the small one, I'll call it P1, is equal to the proportion of the large one. We'll call that one P2. Good?
Wouldn't that just be our H naught in this case?
What was that?
Wouldn't that be our H
Yes,
naught?
it will, but we're going to get to that in a minute. The next thing I'm going to do is I'm going to find kind of the sample and circle it. Researchers found that, okay, so this was my sample, because I don't have another sample somewhere else. So this is my sample. So then I'm going to go directly, like you said, to H naught. And like you said, H naught's always, always, always
Equal.
equals. So it's going to be P1 equals P2. So when we have two proportions, we no longer have numbers in our H naught. It's always going to be that P1 equals P2. So it's going to be, you know, P1 and P2 as my two things here. All right. Is that my claim?
Yes.
What's my claim?
Yes.
P1 equals P2.
Great. Is H naught, what's H naught?
P1
P1 equals P2.
Are they the same thing?
Mhm.
Yes.
Yes. So H naught is my claim. So what am I going to use?
Not equal.
Claim, or am I going to use reject or support?
Reject.
Reject. Because rejecting H naught will reject my claim. Okay, so then H1,
Will be the
what will
opposite.
H1 need to be then?
Not equal.
Not equal. Does everyone understand why? Because since H naught's my claim, how would I reject my claim? My claim is that it's equal. I reject my claim if I find that it's not equal. It can be less than or greater than. So my H1 would be P1 is not equal to P2. Everybody feeling all right with that? Do I check with your neighbors with it? Do I discuss it a little bit? All right, so again, because my claim is that they're equal, then H1, the alternative would be to disprove it, would be the opposite, that they're not equal. All right, so then what is my step 2? What's my alpha?
105.
105. Great, it's right here. Perfect. Step 3, I'm going to do now, how many proportions do I have now?
2.
2. So I have two proportions. Two proportion Z tests, and I got to figure out what to put in. So let's take a look at that. So here's my calculator. I'm going to go to stat test. Do it with me if you can. Stat test. And I'm going to go down to two proportion Z tests. So I'm going to arrow down to two proportion Z test, number 6. Everybody there?
Yeah.
And I'm going to hit enter. Now what do I need to put in? My X1, my small nursing homes. I had, how many small nursing homes did I have?
24.
12 out of 34. So 12 who said yes out of 34. And the large ones were 17 out of how many?
24.
24. And then what was my claim? What's my H1?
Equal.
Not equal to. How easy is that?
Very simple.
Super, super simple. Yep. Calculate. Bam. There's my Z-score. Negative 2.67. And my p-value is 0.00767. So I'm going to write those in. Oh, so first I'm going to put in what I put in here. I did 12 out of 34, 17 out of 24, and not equal to. And I ended up with a Z-score of negative 2.67 and a p-value of 0.004, 767. Okay, great. Next I'm going to find my comparison here, my p-value. 0.00767. I'm going to compare that to alpha, 0.05. I'm going to make them have the same number of decimal places. This one has 6. So I'm just going to add zeros to the end here until I get to the same. Sorry, this one has 5. My bad. So it has 5. So I need to add 3 more zeros to the end of this one. So they have the same, and I can see, oh yeah, 5,000 is way bigger than 767. So my p-value is less than alpha. Am I going to reject H naught or not reject H naught? Check with your neighbors.
Reject.
Reject.
Is it likely or unlikely? Is my sample likely or unlikely?
Unlikely.
Super unlikely. So that means I'm going to reject H naught. So reject H naught. So it means that in step 5, blank evidence to blank claim that proportion of small and large, I should say, I'm going to say vaccination rate, sorry. Vaccination rates of small and large nursing homes are the same. Or you could just take it verbatim. And you could just write that there is no difference in the proportions of the small and large nursing homes, right? With vaccination rate less than 80. Okay. Now what goes in these dashes here? So the first one, again, comes from step 4. So if I reject H naught, do I have enough evidence or not enough evidence?
Enough.
Enough. There's no no, so there's no no here either. They both do not have a no. And the last part is,
Reject.
Reject.
yep, reject, because my claim is H1. I'd use the word reject here. Why? Because my claim is that small large nursing homes, they're equal. And no, they're not. They're totally not. Right? One's like, I don't know, like 30%. The other one's like 70%. They're totally not the same. So we're absolutely going to reject the fact that they're the same. All right, good. So you folks have one to do. Is
No, problem 2.
yep. I'll leave that in there because that's pretty. So lab problem number 2. First, let's figure out what the claim is. I'll give you folks a couple minutes to figure out what the claim is. Your H naught, your H1. And then we'll take a look at part 3. So first of all, what's my claim? Find the concluded part or the question part. That's where we find the claim. So what's my claim?
P1 is greater.
Yeah, the percentage of males is less than the percentage of females. What's up with this 5 days a week thing?
That's how many days they.
Yeah, the more than 5 days a week, is that part of my claim? No, that's just the question that you ask people. Do you work more than 5 days a week? So my claim is that the percentage of males, we'll call it P1, is less than the percentage of females. All right, so then step 1, H naught
Always
is,
equals.
yep, always, always, always equals. Is that my claim? Nope, my claim is less than. P1 is less than P2. So that's going to be my claim. So am I going to use the word reject or support later on?
Support.
Support. Good. Step 2, what's my alpha?
101.
Yep, 0.01. Step 3. Okay, so here I need to find my, all right, so here we have 100 in each group, 7% of males. 100 is my N. Is 7% my X or my P hat? 7%, is that an X or a P hat?
Yeah.
How do I know it's a P hat?
Percentage?
Has a percent sign after the end, right? That's easy to spot. P hats will always have a percent sign after the end, or there'll be a decimal less than 1. So that's my P hat, which means I need to find my X, because the calculator wants me to input an X. So X is equal to NP. So for the males, X for the males is equal to NP. N is 100. What's my little p? What's my p? What's my p?
0.07.
0.07. Yep.
Just 7.
All right. So yep, which is just 7. So then you need to do the same thing for the females, and then plug it all into your calculator to find your z-score and your p-value, and then finish off steps 4 and 5. All right. So step 3. So our x for the females is 100 times 11%. So we get 11. So then we're going to do 2 proportion z-test. 7 out of 100, comma, 11 out of 100, and less than. And you ended up with a z-score of, anyone?
Negative 0.988.
0.988. And a p-value of
0.1615.
1615. Great. So my p-value is not that big, is not that small. It's definitely bigger than 0.01.
So it's failed to
So,
reject.
yep, so we're not going to reject H naught, which means that there is not enough evidence to support, yep,
We claim the percentage of males work less than the percentage of females in
yep,
the
may work less overtime than women. Good.
wow.
All right, good. I will see you folks on